Today I'm going to continue my series on data structures, and I'm going to particularly talk about B-trees. I mentioned in my earlier videos that I was familiar with some kinds of data structures but not with others, and I was doing research to find out how they worked, and I would relay that information to you when I figured it out. And I looked at site after site and video after video on B-trees, and all I could find was abstract theory. So for example, I would see this over and over again. A B-tree looks like this. We have a root piece of data that could split into two other pieces of data, not one, not three, but two, and each one can split into only two pieces of data, and that can work its way down through the tree. Saw this over and over again. Great, very interesting. How is it implemented and where is it used? And all I could find was, well, it's used in SQL. Okay, how does SQL implement this, and where else is it used? And I found nothing after nothing after nothing until I finally found one site that just had a little diagram of a divide and conquer search. And well, I'll just show you what that idea is. Let's say we have a data set, some memory with some data in it, and we need to find a particular piece of data, but we don't know where it is. We can tell if we look at a piece of data if we are higher or lower than that piece of data. So it's numeric data, let's say. So we start in the middle and look at that piece of data and know, is our piece of data a higher number or a lower number? If it's a higher number, we go and split that in the middle again. And then we check, well, is our piece of data we're going for a higher number or a lower number? And if it's higher, we go up. If it's lower, we go down, and we split the difference. And we keep doing that over and over again until we zero in on the piece of data. And when I saw that, I instantly understood what the need is for a B-tree search. And with a little bit of thought, I was able to think about how I would implement that and figured out exactly how that would happen. The reason I understood that is because I'm intimately familiar with how microprocessors work. I've programmed well, at least one of them, and I know how the more sophisticated ones work. And I know the problems of dealing with searching through memory and how this type of search could be implemented to make that much better. So now let's take a look at how a computer does a search. So we have some memory. I'm going to have this 8 bits wide, rather primitive. Today we would have 64 bits, but they're still grouped in groups of 8. We still work in groups of 8 because of the way we encode information. And let's say we're going to look for the name Bob. Keep it all uppercase, just to keep it simple. So, how are these stored in memory? Well, remember earlier I talked about the ASCII code. It's an American Standard Code for Information Interchange, and we encode these letters into a series of bits. So for example, 01000001 equals the capital letter A. 01000010 equals the capital letter B. So every place in memory where we have the letter B is going to be a byte of memory with this binary number stored in the entity that stores, the voltages or whatever that we represent as ones and zeros. And I do not know the O off the top of my head, but I don't need to. I just need to know that these are sequential numbers. So A is in decimal. If I convert that to decimal, I get the number 65. If I convert that to decimal, I get the number 66. And before that is the space. So is the space before? No. Space is number 20. 64 is the @ symbol. That's right. And space is the number 20. And is that 20 in decimal? No, it's 20 in hexadecimal. Oh, lots of number systems to work with, and it's easy to forget these things. But anyway, these are the decimal equivalents. So 65, 66, and of course C would be 67. So these letters all have a representative number, and some of those numbers are higher and lower, and they go in alphabetical order. That helps us facilitate with a search in a way. So let's say we need to search for the name Bob in memory. Let's say it's down here. So I have several bytes to search first. So the microprocessor has to go out, grab that byte, put it in memory, and then compare it to 1011, actually 01000010. Is it that? No. Okay, go to the next byte. Is this one 01000010? Nope. Okay, go to the next byte. Is this one 00 or 01000000, whatever? Is that? No. No. Finally, is this one? Pull it into the accumulator, compare it to, is this 01000010? Yes, it is. Okay, we found that one. Now, actually, I'm going to make this a little more complicated. That's Bill. Bob is down here. So, aha, we found the B. Let's check the next one. Okay, is that an O? Is this equal to whatever the code is for O? No, it isn't. Well, okay, well, now we know that is not right, so let's skip down. Well, we have to check that. And eventually we find, okay, there's a B and an O and a B in sequence. Wow, I mean, we just take a quick look. Yeah, that's Bill, that's Bob. But the computer has to search byte by byte by byte. Now, there might be better ways to do it. For example, we could reserve a certain number of bytes for each name. Let's just do 4 here. And I could start up here. There's Al. As I start my search, is that a letter B? No. Okay, skip to the next name. Is that a letter B? Yes. Okay, check the next letter. Is that a letter O? No, it's not. Okay, skip to the next name. Is that a B? Yes. Is that an O? Yes. Is that a B? Yes. So searching through there, you can see there's some ways we can make it a little more efficient, but still we have to, okay, is that the right starting letter? No. Is that the right starting letter? Yes. Is that the right next letter? No. Okay. Is that the right starting letter? Yes. Is that the right next letter? Yes. Is that the right third letter? Yes. But you can imagine how that would go with a whole bunch of names. Rather an arduous task for something that's pretty simple for us, because we can see things in a way that a computer's just a machine. It doesn't see anything. It can only do what we tell it to do. So that's a rather arduous thing we have to do to look for a name. So let's say we have a database of 15 names. And it's going to take me a while to draw this, so I'll just skip you ahead to right here. So there I have 15 names in this database with their index column. I indexed it from 1 just to help us along with seeing what we're going to do here. But normally that would be 0 at the top. So this is in memory the same way as before. So it's going to be like JOHN and then the index number, then ALICE. It'll have the ASCII codes for those in byte by byte memory, but we've just kind of turned it sideways. So there's a byte, there's a byte, there's a byte, there's a byte, and plus whatever else the name needs. And this would most likely be an index, meaning that we search the index and then we can use the index column to find the data that goes with that index, as I've showed before. Okay, so now let's say that we need to do a search for Linda. How's the computer going to do this? Well, let's say we have the space reserved so it can be a little bit efficient, so it can jump from name to name. So once it finds a mismatch, it can jump down to the next one. It doesn't have to search the whole memory and look for a pattern. It can just do the search as I showed before and skip down. So let's start looking for Linda. So is that an L? No. Okay. Skip ahead. Is that an L? Nope. Skip to the next name. Is that an L? Nope. Is that an L? Is that an L? Down, 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 checking the first letter of each name, going down through the list. And finally we get down to, is that an L? Okay, yes it is. Is the next one an I? Is the next one an N? And finally we found the name. And so we had to search 14 entities just to get to that name. And of course, if there had been something that began with an L up earlier, we would have had to do the comparison. Well, is the next one an I? And what if the name was Lon, L-O-N? Nope, that's not it. So that could have taken even more time. So if we're just searching name by name, let's just simplify it a little and say, okay, is that Linda? No. Is that Linda? No. Is that Linda? No. Is that Linda? No. That. So we had to search down 14, potentially 15 if we were looking for Fred. We would have had to search all 15 names before we found Fred. So that's the problem we're going to have with the database. We can't just scan like we humans can. We have to search letter by letter, and we have no intuition as to where it might be. And so the further down the list it is, the longer it's going to take to make the search. So why don't we make this a little easier by alphabetizing this? So I'll go ahead and alphabetize this list, and there it is, alphabetized. So let's do the search again. Okay, is that Linda? No. Is that Linda? No. Is that Linda? No. No, 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 no. Well, this time it got even worse. It took 15 tries to find Linda, so alphabetizing it didn't do a bit of good. Now, for us humans, we'd take a look at that and, oh, it's L. Let's just jump right down there because we can take a look at the whole picture and process it. We're not like computers. We can process this in an intuitive way and find our way down to it. But as far as computers, they have to do a step-by-step process, and it's still going to have to go through the whole list, and it could take as many as 15 searches or 15 comparisons to find our target. So alphabetizing didn't do a bit of good. But by alphabetizing it, we can now do a divide and conquer search. When we do our search, instead of starting at the top, let's start in the middle. So let's go straight to piece of data number 8 and check that one. Is that Linda? No. But now that these are alphabetized, they are stored as ASCII code, as I mentioned before, which means that each one of these characters, the letter A, is stored as the decimal number 65. Or in binary, it's 01000001. And so every one of these letters has a corresponding number, and the numbers are in alphabetical order. So as we go up through the alphabet, we go higher in numbers. So we can take a look at this first F that we look at and say, well, is that higher or lower than L? Well, that was lower than L, so we know, well, if it was higher, we'd want to search back lower. So we would split the difference, and we would next go and search, well, this is number 8, we divide that by 2, and we would search number 4. And then we would see if that's Linda or not, and we'd decide which way to go. But this time it was higher, so we split the difference and add that to our number. So we divide it by 2 to get 4, add 4 to 8, and we get 12. So our next place to search is number 12. And that turns out to be Jill. But we're searching for Linda. Is Jill Linda? No. Well, what we do is see, well, is it higher or lower? If Linda was lower than Jill, we would split the difference and go up. So we would go up to there, splitting the difference. But this time it was lower, or a higher number, so it's lower in the table. So we split the difference and go there. So we look to see, is that Linda? No, it's John. Well, is Linda higher or lower? If it was a lower number, we'd go back there, but this time it's a higher number, so we go there, and there we find Linda. So that was a divide and conquer search. How many steps did it take? 1, 2, 3, 4. So instead of a maximum of 15 steps to find the 15th piece of data in this table, it takes a maximum of 4 steps to find any particular piece of data. If we drew all of the arrows, we would see that no matter what piece of data it was, it would take a maximum of 4 steps to find it in a table of 15 pieces of data. Now, if we increase this to 31 pieces of data, it would take a maximum of 5 steps. If we increase it to 63 pieces of data, it would take a maximum of 6 steps. So 6 is still a lot less than 63. So if we had 63 pieces of data, do a straight search, we'd have to possibly search all 63 before we find it. But if we do a divide and conquer, it would take a maximum of 6 steps. So if we get a huge amount of data, it still takes a lot of steps, but it takes a lot less than searching the entire table. So that is a divide and conquer search.